Good morning. My name is Wen Huaitao from LSU. This is my pleasure to present our research on today's topics, the global motion of floating platforms with tuned liquid damper in waves. Before diving into all the methodology and results, I would like to briefly introduce the background of our research. In 2018, we proposed an effective solution to resolve the lack of damping of a liquid damper by adding porous media inside the tank. Then we applied the linear and nonlinear potential-based methods to simulate the sloshy fluid wave structure interaction. And compared to the uncontrolled structure, the TLD can reduce roll motion, but is ineffective for heave control, while sway reduction is uncertain. The goal of our present work is to first redesign the liquid damper to further reduce the heave motion of the floater. This is a comparison between the previous model and the present design, where we modify the hull, add mooring lines, and set an internal spring dashpot system between the liquid damper and the floating structure. I will explain our design later. And second, to conduct the hydrodynamic analysis based on multi-phase Navier-Stokes model, as well as developed an interface connecting the fluid and the structural dynamic solvers. Then we can discuss possible applications for complex structures such as LNG vessels, production platforms, and floating wind turbines. In our numerical model, we solve the two-phase Navier-Stokes equation through a hybrid level-set volume of fluid scheme. Therefore, a sine distance function should be given to describe the free surface. To incorporate the rigid body dynamics, we have to compute the pressure and the drag on the embedded surface. Several special numerical skills are applied. For example, the RBVMS method is applied to discretize the Navier-Stokes and level set equations with linear triangular mesh in this study. And one of the IBM, so-called the COFIN, is combined with the equivalent polynomial so that we can apply a higher order quadrature on the cut cell to improve the accuracy. And the Nitsch's method is used in the Galerkin method to ensure the flux conservation in the discrete weak formulation, so the weak numerical stability can be improved. The numerical methods are implemented by our self-developed computational toolkit, Proteus. Proteus is an FEM-based PD solver that is particularly applied to solve CFD problems. It includes multi-phase Navier-Stokes model, dispersive shallow water model, and some interfaces to incorporate other numerical packages. Now we are working on some fast method for the potential flow model, and you are very welcome to check the website and see how it can help your research. And in this study, we will take advantage of another open source toolkit, Chrono, to handle the structural dynamics. We build the interface between these two packages to pass the variable so the solution can be processed sequentially. Some important modules are TP-Flow and the CH-Body for fluid and structural dynamic solver, WaveTool for wave generation, CH-Link for mooring modeling, and coupling FSI for variable delivery. And before the simulation, we have to design the tuned liquid damper properly. In traditional tuned mass damper design theory, two core requirements should be satisfied: the tuning condition and the optimal damping ratio. They are usually related to the mass ratio. in real work, the natural frequency of the floating structure is a known variable. So once the mass ratio is given, we can compute the frequency and the damping ratio of the liquid damper. And therefore, we can adjust the tank dimensions, porosity, and permeability to fit the optimal parameters for sway and roll motions. But the dynamic feature of the heave motion is different. The liquid damper is a dead load along the vertical direction. Therefore, we add an internal spring dashpot system between the liquid damper and the floating body to make the liquid damper a two-mass damper. So the design of the stiffness and the damping coefficient is straightforward. With the concept in mind, we must know the frequency of the floating body in advance. Therefore, we did a free decay test. The structure has an initial 5-degree pitch. The response decays slowly due to the viscous effect around the embedded surface. And also, the induced waves take away its kinetic energy. Then we can characterize the floating structure easily by applying the fast Fourier transform. And in this example, the natural frequency of the heave motion is about 4 seconds and is 2.5 seconds for the other two motions. However, we run up against some unforeseen issue when designing the internal spring dashpot system. The problem is that the heave frequency of the floating body is very low, so the spring has to be extremely soft to satisfy the tuning condition, while it is unable to support the liquid damper. And this video shows the water tank drops so fast to make the system unstable. Therefore, the numerical simulation crashes easily. And we have to compromise a stiffer spring. It is not the best solution, but it still gives us valuable result for the FSI simulation. Here we will present the resonance test with emphasis on the effect of mooring lines and the comparison between the fixed TLD, which is the old design, and the modified TLD. So the first comparison shows how the mooring line affect the structural response. So both structures are not equipped with TLD. And when the mooring line is stretched, it can restrict the horizontal drift. Besides, it slightly reduces the roll angle when the floater is rotating clockwise. The left mooring line will pull it back, and therefore we can observe the tension change with the clockwise angular motion, while the right mooring line is always loose, so its tension is zero and it doesn't affect the roll motion. And the second example shows the reduction of sway, heave, and roll by the modified TLD compared to the moored structure. At first, it slows down the horizontal drift because the sloshing fluid creates a control force in the horizontal direction. For heave motion, even without the best design, the amplitude is reduced. The mean value of the vertical displacement are different because their mass are different. It is also effective for roll reduction. And in fact, the response mitigation of these three motions result from the force cancellation and energy dissipation, which comes from the sloshing fluid for sway and roll, and from the internal spring dashpot system for the heave. The third example shows the comparison between the uncontrolled structure, the fixed TLD, and the modified TLD. So one thing we care about is the additional heat reduction brought by the modified TLD. And it is not obvious in this example. However, with the damping coming from the internal layer, the transient response vanishes quickly. For roll motion, the overall trend are similar. The minor difference comes from the tension of the additional mooring lines and the torque produced by the internal spring. And finally, a few conclusions out of 10. First, the multi-phase Navier-Stokes model can describe complex fluid dynamics, such as vortex around the floater. Therefore, the numerical accuracy is improved. Second, the mooring line can effectively constrain the sway and roll, while the modified tune liquid damper further reduces response in all three directions. Third, in our case, which is a long period floating structure, the design work for mitigating sway and roll is simple. We only have to adjust the tank dimensions. But for heave reduction, the pounding boundary or the nonlinear springs should be applied to avoid the excessive displacement of the damper. In the future, we will focus on uncertainty analysis of the mooring system and the optimal control algorithm for very large floating structures and floating wind turbines. And finally, we aim at developing a hybrid physical-digital twins of wave tanks in coastal and offshore engineering based on our numerical models. Thank you very much for listening. If you have any question, feel free to contact me or find more information about Proteus and our research teams. Thank you.